Welcome to our next lecture in elementary statistics at Dallas College. This is on chapter 11.2, least squares regression. Again, each time we have the objectives here. You might want to make sure they're in your notes, and certainly at the end of the lecture, make sure that you understand these points, which will be on the final screen. In 11.1, we looked at this example before. The table presents the size in square feet of a house and the selling price in thousands of dollars for a sample of houses, for a sample of 8 homes. In the previous section, we concluded that there's a strong positive linear relationship between the size and the sales price. We can use this data to build a model which will then predict the selling price of a house based upon its size. The figures that you see below represent scatter plots of the previous data. Notice the data points are the same on both, but we've drawn a different linear or a regression line. The first one goes up and is very close to each of the points. You can see how the distance from the points, because each point has a little dashed line connecting it to the line we've drawn, the model line. Okay, and so we're trying to figure out which one is a better approximation. If you look at the second one, the distances the points are from the line is quite large. And so the way you figure out which line is better, it's a line that is close to most of the points, that the distance away from the points is pretty far. It's pretty small, I should say, not far. So the graph on the left, the figure on the left is a better approximation. And again, the reason is that the vertical distances, the distance each point is from the line we've drawn, is less on the left than it is on the right. This line is called the least squares regression line. Given ordered pairs, x and y, remember the x values were the size of our house, and the y values were the prices that those houses sold for. And if we calculate the sample means, x bar, all the sizes of the houses, the average, and y bar, all the prices they sold for, the average. We can also calculate the sample standard deviations of all the sizes of the houses and the sales prices. And we can calculate the correlation coefficient. With those data points and calculations, we can then create an equation of the least squares regression line. What this does, it allows us to predict the sales price for any size home that we input based upon the data in our study. So we say that this equation of the line is y hat equals b sub 0 plus b sub 1 x. Okay? This y hat is the equation of the least squares regression line. Okay? All we have to do is calculate a value for b sub 0 and b sub 1, plug it in, and we have an equation of a line. B sub 1 is this calculation. You need to have these formulas in your notes. You need to memorize them because you are not allowed formula sheets for the test. Okay, so B1 equals the correlation coefficient times the standard deviation of the y-axis over the standard deviation of the x. And the y-intercept value, the b sub 0, is the mean of the y value minus b sub 1 times the mean of the x values. Okay? What we're trying to do here is predict selling price based upon any size house. The variable we're given is called the explanatory or predictor variable. That's the size of the house. And the outcome or the response variable is how much it will sell for. Okay? In the equation of the least squares regression line, x represents the explanatory variable or predictor variable, and y represents the outcome. Much like we did in algebra with y being the function value. Okay? So if we want to compute, in this one, try computing the least squares regression line for predicting the selling price from the home. You've got all the data points, you've got all the calculations. Just calculate b sub 1 and b sub 0 and then plug them into the y hat equation. So hit pause and try that. Find b0, b1, and build the equation y hat. When we plug in the values for b1, you can see them all there. I'm not going to read through them. We get 0.09919, etc. for b1. The y-intercept is the average y value minus the b1 we just calculated times the mean for the sizes of the house, the x bar. And there we get 160.1939. Okay? All we do now is plug these two values in, 160.19 for B0 and 0.0991976 for B1. And so this is the equation of the least squares regression line. Y hat equals 160.1939 plus 0.0992x. With this now, and remember x is the size of any house, we can calculate the selling price, the y value that's predicted by our study. Okay. Again, you can see here we've got all your technology will do regression lines, so you can again look in your book for this. And especially if you're doing regression lines in Excel, which you will do in homework, you might want to check out this. They're very simple and short passages. They're only a page or two, and they're very step-by-step with examples. Okay. So the reason we do these regression lines is so we can predict other data points that we didn't collect real data on. And often what we'll do is we'll check the calculated value and see if we can find another house in that near range to see if our model is standing up. So remember, here is our least squares regression equation. So I want you to calculate the selling price of a house of size 2,800 square feet. So hit pause, do that very simple calculation, and then come back. Remember, the selling price of a house represents the x value. That's the only variable we need to plug in because we want to find the predicted selling price, which is the y variable. So we just plug in 2,800 for x and calculate. So based upon the data we collected and having a strong positive linear association with a correlation coefficient of 0.90, we predict that a house of 2,800 square foot should sell for about $438,000. If you plotted that, you would see, because we made an equation for our line, of course that point and any other calculated point is going to be on the line because this is the equation of this line. So it makes perfect sense that the value we just calculated is on the line because that's how we calculated it. We created an equation for this line. In the house data, the average size is 2,891.25, and the average selling point is 447.0. Okay? If we substitute the 2981 into x, the average value into x, and calculate the y value, notice we get the average y value. It absolutely makes sense because we created this equation using those average values. That is, for a house of average size, we predict that the selling price will be the average selling price. I mean, that's kind of circular logic if you ask me. In general, the least squares regression line goes through the point of averages x bar, y bar. Doesn't always happen, but because we're using those, most likely the averages will be on that line. The predicted value y bar can be used to estimate the average outcome for a given value of x. The equation of the least squares regression line for predicting the selling price is here. We've been using that. Use this equation to estimate the average price of all houses whose size are 3,000 square feet. Okay. And then try writing your answer in sentence form. This is very typical statistical practice. We not only present some data numbers, we write it out in a sentence to make sure that people are interpreting that value in the correct way. So when we plug in the value, we get 457.8. We estimate the average price for a house of 3,000 square feet to be $457.8 thousand. Okay. Again, notice how that sentence is very clear. It's very simple. It's declarative. It shouldn't be long, hopefully. Otherwise, you get more convoluted. Now, what about the y-intercept b sub 0? Now, remember, hopefully, from your prior math and your algebra, the y-intercept is if you continue that line down to the point where x equals 0, that line should cross the y-axis at some point, and there's a y value there. The y-intercept value, the b sub 0 that we calculated, can have a very practical interpretation, but only if a 0 value for the x variable makes sense. Okay? In our example, remember, the x variable was the size of a house in square feet. So it makes no sense for us to interpret the meaning behind the y-intercept, because this would be the selling price of a house that had 0 square feet. Well, if you have a house with 0 square feet, you don't have a house. Maybe you have an imaginary house, okay? So if you're going to interpret the y-intercept, you only do that if x equals 0 has some kind of relative meaning in terms of the study that you're doing, okay? If data contains both positive and negative x values, this is typically when the y-intercept, which is the estimated outcome when x is 0, does have some kind of context, if you will. If all the x values are positive, or if all the x values are all negative, then typically there is not a useful interpretation. And again, I've already gone through this. In our house cost example, the y-intercept would mean the selling price of a house was 0 square feet. So of course it makes no sense at all. What about the slope, b1? If the x values of 2 points on a line differ by 1, their y values will differ by an amount equal to the slope of the line. This enables us to interpret the slope b1. If the values of the explanatory variable differ by an amount d, then their predicted values y will differ by b1 times the slope, d. I'm sorry, the slope, which is b1, times the difference between two x values. And that's just the slope formula. Slope equals the difference in y values over the difference in x values. So if you're trying to figure out a difference between two y values, and you know the difference between the x values, you can multiply that by the slope. I should have put that formula in there. It's easier to see visually with the slope formula. M equals y2 minus y1 over x2 minus x1. If you multiply both sides by that denominator, x2 minus x1, you get something called the point slope equation of a line. Two houses are up for sale. One house is 1,900 square feet in size, and the other is 1,750 square feet in size. Okay? By how much should we predict their prices to differ? So we're going to use this little formula here in yellow, B1D. The difference between the x values times our slope, and that's here, that 0.0992. Remember that, okay? So try this calculation. 1900 minus 1750 is 150 times our slope, and we get $14.9 thousand. So we predict that the difference in selling prices for these two homes, which have a difference of 150 square feet, will be roughly about $15,000. Okay. At the final exam in a statistics class, the professor asks each student to indicate how many hours he or she studied for the exam. After grading the exam, the professor computes the least squares regression line for predicting the final exam score from the number of hours studied. The equation of the line is y bar equals 50 plus 5x. Anton studied for 6 hours. What do you predict his exam score to be? Emma studied for 3 hours longer than Jeremy did. How much higher do you predict Emma's score to be? Okay. So see if you can do these two problems. All right. Hit pause, try them, and see if you can do it. Well, remember, the number of hours studied is our x variable. So to answer the first question, we need to just plug this answer into our linear regression so we can see what the predicted exam score would be. Okay? And we get 80. So if Anton studied for 6 hours, we would predict that he would get a score of approximately 80. Okay? Emma studied for 3 hours longer than Jeremy did. How much higher do you predict Emma's score to be? Now, this is the case where we know the difference between two x values. She studied for 3 hours longer than Jeremy did. So remember, we can just plug in the 3, the difference between the two x values, times the slope. Where's the slope here? Do you remember? It's the number in front of the x, 5. So to calculate this, we just take the slope times the difference, and we would assume that Emma's score should be about 15 points higher than Jeremy's because she studied for 3 hours longer. Again, here's the things we just covered in this lecture. You might want to hit pause, make sure you understand how to do them, and of course you can always go back and review the slides again or the lecture.